Today we are going to round out the assessment module with a couple of, just talk about a couple things, evaluation and ethics. Hi, Toots. Can I help you? Sorry, we have a special guest today. Oh no. Okay, sorry. Hi. Thank you. I appreciate that you love me, but now is not a good time. Okay, sorry, I guess this is just life. So I'm gonna just keep going, or start. So yeah, this, shockingly, is gonna be about 2 chunks evaluation. How do we assess our claims? And some basic ethics. So 2 objectives. We'll discuss evaluation using significance testing and effect sizes. And then we'll talk about some of the ethical issues related to assessment. And I swear this is the last kind of chunk on statistics. I know that this is not what you signed up for. Well, you didn't know you were signing up for it. So yeah, let's talk about what significance testing is, because it's going to come up. You've likely heard it in really any science class, or well, any social science class, that something was statistically significant. What does that mean? So in it, guess who's sitting on the keyboard? Tooks. Excuse me. Hi. Well, let's get back to, nope, that's not what I want. Okay. I'm going to keep this in because I don't feel like resyncing. Alright, so here's where we were. Statistical significance. Oh, we've moved on. Okay, so he'll probably be back. But yeah, that's Tukey for you. So statistical significance is this idea that a result is real, that it's meaningful, that it's not, but from a more technical standpoint, what it is a probability. It's the expected, so it's a percentage almost. That's how you can think of it. So it's this idea that a result would only occur by chance, and we can decide what the rule is, but in psychology it's 5% of the time. And that's the basic idea. You want your result to be meaningful and not just random chance, but things happen, unusual things happen. So as a field, personality psychology and most of psychology has decided that 5% is the number we're comfortable with. So we're okay with 5% of all the things we say are statistically significant, are meaningful, that it's the benchmark we shoot for papers, that 5% of the time, so 1 in 20, which is actually a little more strict than the original paper that looked at that made this kind of rule. There it was 1 in 18 or something. It doesn't matter. But that 1 in 20 times the result we found, and we don't know which one, could have, that 5% of the time we expect the result to be because of chance. So if you do 100 studies, 5 of them probably false positives. Now we do all of this within a null hypothesis statistical testing framework. Now, for the Bayesians in the room, I'm sorry, we're covering a frequentist approach. I'm happy to talk to you about what the difference between Bayes and frequentist is. I'm agnostic. I tend to publish with frequentist approaches because that's what psychology does. But I really like the Bayes stuff. So null hypothesis significance testing, NHST, is the traditional method of statistical data analysis. It's got that whole, like, how unusual is this statistical result that we got? And other areas have a little different phrasing. And the biggest challenge here is, like, how backwards it feels instinctively. So what null hypothesis statistical testing does is determine the chance of getting the result that you want. Like, you pose a null, which is nothing happens. So compared to a baseline of nothing was actually happening, like there was no real effect for your study, the chance of getting a result that looks like something's happening, we use the rule of 5%. Other fields like neuroscience tend to raise the bar by making their false positive rate 1 in 1,000, 1 in 100, 1 in 20 is the lowest that you can really go and get away with it and like be able to justify like your p-value, which is what it's called. So there are a lot of criticisms of this method. I think it's more of a problem with research process than the method itself. I think if people really understood that this is it's 5%, so you should replicate everything, we would be okay. But there's a lot of criticism because people don't do the stuff you're supposed to like replicate your findings to make sure that it's not that 5%. So p-value, or as the book calls it, a p-level, is the probability of obtaining a result from a statistical test if there really is no difference between the groups or no relationship between the variables. There's some nuances here, but this definition is not incorrect. And it gives you the basic idea. There's way highly super technical definitions that I'm happy to talk to you about, but you're probably not happy to hear about them. So essentially what significance testing is telling you how unusual your data would have to be, or how unusual your data are, if there's actually nothing to see here. Like, that's why people are more impressed by p-values that are really tiny, so like p less than 0.001 suggests that the data are really, really unusual. So the more unusual it would be, the more likely it is not to have that been the case. That's the idea. So there are problems with this, big problems, and there's just like the field is kind of reacting at this point, so it's probably a healthy medium. But right now we're in a sizable chunk of people really want to do away with this technique because of these limitations that people don't tend to remember. So significant doesn't mean strong. It doesn't mean important. It means how unusual it is. That's it. And there's no such thing as very significant or like kind of significant. It's a decision rule. Either it's past your 1 in 20. We'll see if I don't think I'm going to bother doing an animation because you'd rather have these videos out, I think. But it's a cut point. It's a decision rule. There's no like wiggle room. Either it passes the bar and it's more, so it's less than that 5%. So it's below our rule. So it's more unusual than we would, like, it's an acceptable level of false positive. if it passes that, so it suggests that this would have to be like even more unusual. So say it's p equals 0.03 under a decision rule of 5%, we would and here's the so we would reject the null, and the null is that there's nothing happening, that there's nil. There's no meaningful effect of your experiment. So the p-value of like 0.03, so 3%, we're willing to risk it. That like there's only like that 3% is low enough that we're okay with it. We're like, okay, it's probably not the case that nothing is happening. That's it. And if you are above that, so if you have a p equals 0.051, you are not unusual. Your data are not unusual enough. So you can't reject your null. And there's some language that makes this a pain in the tuchus. Can I say tuchus on YouTube? Pain in the tuchus. That, like, right, if you're on that border, like that 0.051, it is not unusual enough. We have to, we can't say, well, it's unusual, like, you can't reject the null, is the language that we typically use. There's other versions of this called, like, failing to reject, which is, I don't like, because it implies it has a value judgment. But in psychology, we really want to reject the null. So when we say something is significant, that means we rejected the null, and that we are comfortable with that level of chance that it's a false positive. Unfortunately, people don't view the a p-value as a yes-no. They interpret the number instead of viewing it as a decision rule. The criterion for 0.05 is pretty arbitrary. Like, that's not even what Fisher used. His ends up being like 0.0625 or something, which, so 5% is arbitrary. What if we put it at 0.06? Then that study that, like, some psychologists will call marginally significant because it's really close and they really, really, really want it to be significant. They really, really want it to, because then they can publish their paper. You have, that doesn't cross the threshold. Or the 0.05, but it crosses a 0.06. So, and it's just 1% difference between those two rules. And it turns out there are things that influence, like, how small your p-value is, that it doesn't have anything to do with how big and strong your effect is. I could have a super significant result. Again, this is the social psych language talking. Like a result that has a p of less than 0.0000001. So, like, super unusual. Like, you see this with, like, DNA results. Like, the chance that, like, he's the father is, like, there's a significant chance that he's the father, and, you know, I mean, they don't talk about the probability but it's still a probability, like, of paternity. It's hard. And sample size has an effect. So if you collect more data, even if your difference between what, like, business and as usual, so, like, no effect, and, like, the teeny tiniest effect ever, like, I use the correlation between height and intelligence as an example, because I've seen papers where it's really significant, and it's because their samples are huge. But if you were to look at, like, what the correlation is, what the association between those is, it's 0.05. If that. It's tiny. It's barely, like, height is barely predictive of intelligence. And it's because the genes are next to each other. Well, there's some height genes that sit next to some intelligence genes. We haven't found all the intelligence genes. We haven't even found all the height genes. But that's the idea. So, like, they move together. because they're literally next to each other on the chromosome. It's cool, I think. But when you have huge samples, you can get a significance level that's super tiny, itty bitty, tinier than the correlation between height and intelligence. So it doesn't tell you anything about how meaningful the effect is, like how big it is or how important it is. Because some metrics, like, you need a really big effect for it to make a difference. Like the difference between, while in other cases, like a tiny little relationship can have huge difference. So let me do a tiny effect example. Like the relationship between anything in longevity. So if you can improve people's like exercise routines and get like if you marry an active spouse, the spouse will make you more active. And like, so having an active spouse like can add, like, even though the effect is small and tiny, can add even just 6 months to your life on average. 6 months is a small effect in the scheme of like 100 years. I mean, obviously we don't. Like 6 months, so half a year, is a tiny effect. But it's pretty meaningful, like even like one extra month to live. Be awesome. Because most of us like living. So significance conveys how unusual the data is, and that's it. Compared to like business as usual. That's it. And if you read into it more deeply, like, ooh, that one's very significant, or that one's marginal, it defeats the purpose. That is not what significance testing is for. Sorry. I have strong opinions. So, yeah, so more problems with null hypothesis testing. Non-significant results are often interpreted as no result, so that the fact that it's non-significant means that there is no relationship. That is not what it means. It just means, so like if you have a p-value of 0.1, so 1 in 10 times that was just by chance, that means 9 out of 10 times that non-significant correlation is still meaningful. It just provides information about the probability of errors. Now, you'll notice I like to be a little grumpy about and disagree with. I highlight that it's a purposeful teaching technique to highlight that there are disagreements in the field, that nothing is set in stone. Even something seems so obvious and simple and like procedural as statistics has nuance and debate. So that's why I do it. That, and I also disagree so I'm going to tell you. So the preamble for this is I don't like the terminology type 1 and type 2 error because they are unintuitive. Type 1 error is a false positive. What it is deciding that one variable has an effect so that there is a meaningful relationship when there really isn't one. So you say it's true. You say that there's a true relationship between height and intelligence. But in reality, so like that's the decision rule. So our p-value maps onto type 1 error, which is a false positive. So you're saying it's real when in fact it's not. Now type 2 error is deciding that a variable doesn't have an effect on a relationship when it actually does. So in this case it's the flip. So you say it's true, that it's not true, but it's actually real. So like that would be me saying, oh, and in this world correlation between height and intelligence is real. Oh, it's not significant. It's not a thing. But in fact it is. It's a tiny correlation, but it's still real. So it's a trade-off. So a type 2 error is a false negative. Type 1, false positive. Type 2, false negative. Way easier to remember. Unfortunately, many psychologists really love this terminology because that's what they were taught. So they will teach it to you, and they will expect you to learn it and teach it to the future. Even I am teaching it to you because other people use it, and I don't want you to be underprepared. But the heart of it is type 1 error, false positive. Type 2 error, false negative. So when you have a non-significant result, it is hard to tell if it's a false negative. Because while our p-value is great at like giving us an actual number of, okay, here's how unusual it would be in a world where there's not actually a relationship. Type 2 error isn't built nicely in, and it turns out to be like way higher. And like the rule right now, and of course I have problems with this because I have a problem with everything, is 20%. 20%. So 1 in 5 studies won't find something that's there, which is pretty expensive. Now the flip of that is, for the flip of type 2 is power. And so that's the ability to detect a meaningful result and actually say it's meaningful. Power. And we have a problem with psychology. The fact that we can only find so essentially we find the effect if a study is, like, we're okay with only finding the effect 8 out of 10 times, 4 out of 5 times. Which I think is pretty expensive. And so that's the ideal. Most studies are very underpowered, so they don't have the ability to. So it's almost suspicious how we find so many significant results. More so finding significant results than we should from a power standpoint. So it's hard to tell because there's no like magical built-in like number the same way a p-value is, if your result is stable or due to chance, and even if it's significant, it could be just not important, like height and intelligence. Sorry, I read a couple papers on it like really recently, so that's my shtick right now. So what's an alternative? Effect size. I mean, it's not really an alternative. You should use both, please. All these alternatives suggest that, like, use one of them. Use both. There's no either or here. Just use both. It's helpful. Effect size is an index of the strength of the relationship between two variables. Or, like, there are other ways to quantify it, but in personality, we're going to use correlation a lot. And so one example of an effect size is a correlation. And a correlation can be used in either experimental or correlational studies. But it's a useful metric. And you'll notice that I've accidentally slipped into using it because I find it very helpful. It quantifies the strength of a relationship as well as the direction in a really nice way. So a correlation can be between -1 and 1. If you see a correlation outside those bounds, it's a covariance. Covariance is standardized correlation for the stats people in the room. That's it. Or a correlation is a standardized covariance. Sorry. Okay, so correlation coefficient is probably the most commonly used effect size. Like if you asked me to name one, I think that's the one. So it measures the relationship, and correlations less than 0, so negative correlation suggests that there's a negative association. So when you move up, so like increases in smoking are linked with decreases in longevity. So more smoking, less of the other thing. So that's a negative association. I've got a picture on the next page, but it's a diagonal down. Positive association, correlations above 0. And the closer to a 1 or -1, the stronger it is. The more like predictive the association is, the more close and tightly together your data are. So positive associations like well, not everything is linear, but like number of ice cream scoops or eaten, positively associated with happiness. Stuff like that. That's a lame example. Or how about this one? The likelihood that you are a cat lady is positively correlated with the number of cats you have. There we go. That, I think, is a really strong correlation. But that's the idea. And so stronger correlations are closer to the edges, and weaker correlations are closer to 0. Correlation of 0 means there's no relationship. Okay. So here's some illustrations. There's a fun game that I play in my intro stats class called Guess the Correlation. And I do it live in class so that sometimes I practice first because the first round is awful because it's hard. It's easy to be like, oh, perfectly correlated. -1. It goes straight down. 1 unit increase in X is associated with a 1 unit decrease in Y. A negative correlation of point -7, pretty close together. I know you've seen these. I'm just hammering it home again because it's helpful. No correlation, there's no noise here. It's just a square blob. There's, you could try, there's no systematic line. Here, 0.5, the dots are pretty close together, not super close, not as close as this guy. And here's perfect correlation. The dots perfectly lined up. So it's great for prediction. And interpreting the effect size, though, there's some disagreement, and David Felder has very strong opinions on this, and he's the only one that teaches this technique, but it's a useful one. It's not unuseful, so it can be used for prediction. So a 0.25 correlation, so a small to medium, explains 25% of the variance in an effect, in the relationship. So, but it's kind of hard to know what that means because it looks tiny. And because even a big correlation, say you have 0.9 as correlation. What you do is, so you square root it to figure out what the variance explained is. So a 0.9 correlation means you explain 81% of the variance. A 0.9 correlation is huge. It's it's really tightly lined up. And that's only 81%. People would, in America, not in this class, but in the United States, that's a B-. But it's amazing. So it's not an effective, metric. So it's not, it gets misinterpreted and downplayed. Binomial effect size display, which I will keep spelling out the acronym for, is one method to kind of compare across different kinds of standardized effects that convert a correlation into into an effect that looks closer to an experiment. So that when you're talking to experimentalists, if you have correlations, they just see that 0.25 and they're or that 0.3. I cannot talk. This, a tiny correlation, the tiny number. Be like, oh, that's small. 6 is tiny as a number. So clearly your work sucks. While I have these big numbers of and percentages where we can accurately predict. I'll show you the picture in a second, but it's a way to understand the magnitude of a correlation and kind of help intuitively. This is not a universal opinion. I love R-squared, but I know how to interpret it because my advisor's specialty was literally the correlation. Yeah. So, here's the basic idea. Assume you have 200 participants with 100 in each group. What you do is concretely display what a correlation is in terms of a specific outcome. So, and Anova Studies have the same structure. So here we have a correlation of 0. each of these cells has 50 people in it. So the drug had no effect. So 50 people lived who took the drug, and 50 people lived who didn't take the drug. Same way as the other way. People who took the drug, 50-50. Out of 200 people, half live, half die. Correlation of 0.3. You know, that's not huge. And if you were to, like, take the square root of that, it would be a number a little less than a number that I might put here. That is an exercise I will leave to the watcher. But you can convert this by just popping in, by multiplying the correlation by 100 and dividing by, I think it's 2, the number of groups or something. You're not going to have to be able to do this calculation, but it's the idea. And so a correlation of 0.3 shifts your study, your finding from, so 35 people lived who took this drug, or no, 30 people died who took this drug, while 65 people lived. That's a 15-point difference here. So if they didn't take the drug, only 35 of them lived. And that's a small correlation. So it allows you to, like, that's a 30-person difference, which is coincidence. Okay, it's coincidence these numbers work out that way. So that interpersonal sensitivity, you still have to interpret these generously. It's not causal in this sense. But 0.25, 63 versus 78 with a magic person added. There's a big difference. It's almost double. I mean, it's not really, but like, if you eyeball it, it's pretty close. And that's a small effect. So that was this. So that's our last little statistics unit. Unless you want more. I know you don't. I've read the course of Vales. But yeah, so that was statistics. Next time, for you at least, we're going to talk about some ethics. And I like to talk about the research ethics piece because I think it's really important. And I know you get this in a lot of classes. But it's like, wouldn't you be a little horrified if no one talked about it? Okay, well, that's my thoughts. So I will see you next time. Like and subscribe and check the bell icon. No, please don't. I'm kidding. Yeah, so next time we'll cover research ethics. And hopefully Tukey will not sit on anything.